we'll start with the general idea of carbon neutrality, like what is it all about? And then we will focus on urban soil research, challenges and perspectives. And then we'll go into more details about carbon stocks and fluxes in urban soils. And finally, how they interact with the climate at different scales. So to begin with, have you ever heard about the IPCC? And I'm not sure I can see you well, so if you have heard about it, just let me know somehow or speak up, because I think I hear you pretty well. Yeah. So IPCC, that ring the bell? Yeah. No? Okay. So it's an intergovernmental panel on climate change. They got a Nobel Prize in 2007, and well, more than 1,000 of scientists working together to understand what's going on with the climate and what are the perspectives, etc. And they deliver, well, lots of nice reports, but the main reports are delivered each 6 years, if I'm not mistaken. And one of the most recent ones was delivered in 2023. And among many other impressive outcomes, it was mentioned probably one of the first times that urban areas, that cities become, let's say, hotspots of the climate change. And not only because they are important sources of greenhouse gas emissions, but also because urban ecosystems are really vulnerable to climate change. So that makes us think a lot about climate mitigation and climate adaptation strategies and how they can be implemented in cities. Yeah, as soon as you are familiar with IPCC, you probably are also familiar with those graphs and maps. They basically show how temperature is increasing and what can we expect from different scenarios globally. And this is probably one of the main pictures. So this is the projection of the cumulative CO2 emission and corresponding increase in temperature for different SSPs. Yeah, so SSP is kind of the scenario, the pathway, more positive or more negative, or let's say considering different changes in economy, first of all, so more going as business as usual, and that's a more negative scenario, or more oriented on, let's say, environmentally friendly and climate mitigation strategies. So there are 5 main scenarios, or 8. One of them is subdivided into 3 sub-pathways. I just give you short description of 2, probably the most extreme. And then SSP1, sustainability, taking the green road. Yeah, it proposes low challenges to mitigation and adaptation. So basically that the world shifts gradually and starts focusing on, well, say, the alternative energy sources and green economy, etc. And an extreme, the kind of opposite to that, it's SSP5, fossil fuel development, taking the highway. So basically we don't care that, or we do not care that much about climate changes, and we care way more about the economy, and we keep doing the most profitable development, let's say, with the minimum or limited attention to environmental consequences. Well, clearly that the outcomes of those 2 on environment and on climate change, first of all, would be different. Who of you think that SSP1 is the most likely? Likely, yeah, likely. So you believe that SSP1 will be implemented? No, not that much. SSP5? Yeah, probably also not. So probably we'll try to balance between those and find a smart way to combine the economic and, let's say, ecological needs. So this is what all these smart guys from IPCC, but with a even more important, what is even more important, like governments during the conferences of parties and different other kind of negotiations try to find, but that's of course not that easy. And regarding to all these scenarios, we get familiar with the concept of the carbon neutrality, because actually, as you saw, the two main parameters which are discussed is the mean annual temperature, which is increasing, and greenhouse gases emissions, but first of all, carbon emissions, which are also increasing, and the relationships between them are rather close. So we can be quite sure that carbon balance has something to do with the climate change. And depending on what we expect from the scenarios regarding the balance between carbon stocks, carbon sources, and carbon sequestration, we can be more or less, let's say, positive about those scenarios. So you can see that from all the scenarios, only two, and actually one, because these are the two subparts of the SSP1, they assume that the carbon neutrality can be achieved. So basically, if we want to be carbon neutral, and if we believe, as soon as we believe that carbon neutrality is kind of the main solution for to mitigate climate change, then SSP1 shall be our target. And that's more or less kind of the global concept that are now considered. This means that we shall care a lot about carbon balance and carbon sources and carbon flux. And this is kind of the very general estimate of where carbon is coming from and where it is stored. So you see that there is lots of carbon in the atmosphere, but at the same time, it's quite dynamic, so it cannot be there for a long time. And there is more carbon in oceans, and in terrestrial ecosystems, most of the carbon is stored in soils. And basically what we want is to take carbon from the atmosphere and capture it in the ocean or in soils or in biomass for a long period of time. That's a very simplified story about the carbon sequestration regarding the carbon neutrality concept. What we also can do, or probably what we first of all shall do, is to consider what are the main sources and what are the main sinks, and how can we affect those sources and those sinks. While the main source of CO2 is clearly an anthropogenic source, could be industry or traffic, or let's say everything we do, but also 14% are coming from indirect anthropogenic effects, for example, from land use change, deforestation, etc. And for the sinks, we have atmosphere, terrestrial ecosystems, plants, plus soil and ocean. So if we want to keep the balance, we shall either reduce the sources or try to increase the sinks. So the carbon neutrality in general, the very general carbon neutrality equation can be presented like this. We have different sources, anthropogenic sources, also natural sources, because we, of course, have respiration, soil respiration, plant respiration, in total ecosystem respiration. We have emissions with volcanoes, with forest fires, etc. So all these contribute to the huge carbon outflow. And at the opposite side, we have carbon accumulation in biomass and further carbon storage in biomass, water, soils, and sediments. And we can further subdivide those in sub-fluxes and try to see how the quantity of incoming and outgoing carbon can be balanced. Well, this is kind of the theory, but this theory is more and more used for regulations, national and international standards, of course, international agreements like Paris agreements, which we now keep referring to. And depending on the country, the agreements can be more or less strong. In Europe, they are quite strong. I would say we have the European Union climate law, which is based on the Paris agreements, and basically this climate law assumes that the climate neutrality target shall be achieved by 2050. There is the European Green Deal. This is basically kind of the roadmap how the carbon neutrality shall be achieved. And there are lots of measures, and many of them are not really popular because they can also bring the economy down. For example, at the end of the 2023, the carbon border adjustment mechanism was implemented. So that means that if in your country the carbon neutrality legislation is lifted in comparison to the European legislation, then to export your goods, you have to pay for that. And I remember that a year ago, so there were many Russian manufacturers, first of all, working with fertilizers, with aluminum, so with this kind of resources. They were really afraid of this law because, yeah, for them, that would mean considerable costs. Yeah, well, later on, it happened that it was not the main problem for them. But anyway, understanding of the fact that you have to pay for carbon neutrality is very obvious in Europe and not only. And that means that we shall be quite accurate with the calculations of carbon stocks and fluxes, because that's not only the like our scientific stuff, but really the thing that people are paying for. And in this regard, yeah, we're thinking about, okay, we have to pay for emissions, so that's clear, but probably there are also ways how we can compensate those emissions. Yeah, and we can plant trees, for example, and do some other simple things, but we can also implement it in the everyday activities. And as soon as we are talking about cities, then clearly we can expect a lot from urban green infrastructures, because on the one hand, cities are sources of emissions. There are lots of traffic or industries, etc. But on the other hand, we anyway invest a lot in urban green infrastructures, in the public green spaces, parks, community gardens, etc. So let's try to benefit from that. Let's try to consider those green infrastructures as a solution. We can also call it nature-based solutions for carbon sequestration and for climate mitigation or climate adaptation, or both. And the document you see on the screen, this is the roadmap for climate progress, which was proposed by US party at the conference of parties last year in Egypt. And yeah, you can see that there are many solutions which are the regular parts of urban green infrastructures development and maintenance and landscaping. For example, there are green roofs, urban trees, urban forests, blue-green infrastructure, etc. So basically, we worked quite regularly with the landscape architects who are using these kind of solutions, but without really paying attention on how beneficial could it be regarding the environmental functions, and first of all, regarding the carbon balance. And this kind of roadmap and also the, let's say, tools under it provide such an opportunity. How can we do that? Yeah, let's zoom in a little bit in the carbon balance. So we are not talking about like global carbon balance anymore. We try to focus on the biogenic carbon balance and try to adapt it for the conditions of urban green infrastructure. So the biogenic carbon balance, yeah, when the anthropogenic component is excluded, is basically how much carbon is captured and stored by below ground biomass and then accumulated in soil, and how much carbon is emitted by soil respiration, or more specifically by heterotrophic soil respiration, by soil microorganisms, because there is also the autotrophic part of the soil respiration by roots, but this one is compensated by the carbon sequestration in biomass. So if we come up with a very simple equation, or ratio, which is more widely used. We need to know, sorry, how much carbon is stored in biomass in soils and how much carbon is emitted by soil microorganisms. When we know that, we can come up with an idea of the carbon balance. Well, this is a conceptual idea, but this conceptual idea is getting more and more implemented for practical solutions. And these are several case studies which, well, I would say with more or less details that utilize these concepts. For example, this is the Urban Green Life project. That's the European Union funded project, but there were many private companies and NGOs involved. And they developed, at least for two cities, for Krakow in Poland and for Rimini in Italy, this kind of detailed databases where for a particular park or for several green areas, all the trees were mapped. And for each tree, dependent on the species and dependent on the condition, you could really see the expected carbon sequestration and also some other ecosystem services. So, for example, this is the park in the center of Krakow, and you can click on the tree, and if it's a Norway maple, you can see like how much carbon is emitted and also how much how much carbon is captured and how much dust is absorbed on the leaves. Yeah, so this is kind of an approach which can also be further developed, linked to the monitoring tools. But the main idea is that when we develop a park, when we even plant a tree, or when we select between a tree and another tree or tree and a shrub, we can base our decisions on understanding of the expected effect on carbon balance. Well, this is another approach, but more or less about the same thing. It's kind of the next step. This is the I3 model developed by David Nowak from USDA, I think, from Forestry Department. And well, this model is very popular among the urban ecologists, let's say, because it actually allows estimating ecosystem services for urban green infrastructures. And when you have the tree survey and you have the meteorological data and some other parameters, which is possible to get, you can even map ecosystem services for the whole cities, like you can see here for the case of Tbilisi in Georgia or Beijing, or you can also make comparable evaluation of scenarios. So lots of things you can do. And also among many ecosystem services, carbon sequestration is always there. Yeah, so by this or that way, you can estimate the let's say, carbon effects of urban green infrastructures and try to consider it for, let's say, climate smart, climate resilient urban development. What is interesting that almost none of those tools really care or consider urban soils. Yeah, so basically we plant a tree and we can estimate how fast the tree is growing, and depending again on the species, on the condition, on many other factors, including soil, but we do not really consider how much carbon is stored in soil or how much carbon can be emitted from soil. So yeah, well, some models of course have this part, but it's really not detailed. And when we talk about urban soils, then we get almost lost. So that's quite a problem, because when we give our estimates of carbon sequestration only based on the above ground biomass, and we keep in mind that carbon respiration is quite a important carbon outflow, then probably our expectations from urban green infrastructure can be too high. Yeah, maybe we overestimate carbon sequestration potential if we do not consider soils. And there are quite some papers which actually confirm that, for example, for the case of I3 in Italy. So let's try to get some idea about what's going on with carbon in urban soils. But first of all, what we generally know about urban soils? Well, since you already met Maxine, I think that this is not the first time you hear about urban soils, so I probably will skip some general slides also to save time. But let's say for many years, urban soils were really not the main focus of soil scientists globally, partly because there are not too many cities. Well, I think there is more than enough, and urbanization is rapidly growing, and this is what you can also see from the UN reports or from the nighttime light imagery. But of course, if you compare the total area of cities to the total area of forests or deserts even, then yeah, they are not making the main contribution, at least in terms of the extent. The other reason, of course, that urban areas are really heterogeneous. So sometimes it's impossible or very difficult to predict what kind of soil can you expect under urban lawn or under a tree or on the pavement. Moreover, there are some people who just don't believe or don't care that there is some soil under, well, in cities. Because if we think that soils are mainly for agriculture, and if we forget about urban farming, which we shall not probably, and then we can say, well, yeah, indeed, who cares about soils in cities? We have roads and houses. There is no space for soil, or at least we do not really use it. Yeah, well, for me, that's quite a, well, I would say primitive or not really scientific approach. But yeah, well, you can believe that for many years this approach dominated, and really the focus on urban soil in research, yeah, to say nothing about the practical aspects, started more or less in 1990s in Germany, in US, in Russia, and well, in France, and then it continued going. Yeah, from the general ecosystem approach, we of course consider soil as a very important component, usually one of like 5 key components. And in this regard, when we talk about urban ecosystem, it's still there. Yeah, so we have urban air, urban water, urban sediments, and we also have urban soils. And those urban soils are clearly anthropogenically affected. Yeah, there are different, let's say, views on how can they be classified, from man-changed to man-made to the artificial urban soils, which have nothing to do with the, let's say, natural soil forming factors. But anyway, when we talk about an urban soil, well, we have a man somewhere around, and we have interrelationships between a man and urban ecosystems, direct through environmental impact, and also the opposite, when ecosystem services can be produced by urban ecosystems and they affect human well-being. Okay, so I hope that you have heard about this guy, Vasily Dokuchaev, whom Anna and me are proud to be the same country from, because from soil scientific point of view, he is well recognized as a founder of genetic, yeah, classical soil science, and it was not that long ago, yeah, more or less a century. And one of the basic principles which are still used in any kind of soil research is the idea of soil forming factors, which are climate, biota, relief, burn material, and time. And when we talk about urban soils, we of course add anthropogenic factor, because anthropogenic factor can have a direct effect by soil pollution, for example, or by soil compaction, or by soil sealing, or by soil construction, but also indirect influences. Like one of the topics of the final part of the lecture will be about how urban heat island affects urban soil carbon. But urban heat island is, of course, the indirect anthropogenic effect on soil, because urban heat island is a kind of the mesoclimatic anomaly which occurs in cities because of the anthropogenic effect of the built-up areas, etc. And similarly, we can say that sloping and landscape planning, landscape design, they all have clear effect on how urban soils look like? Well, these are some definitions. Yeah, I don't know how much shall we go into the details, but just to give you an idea that it's not that obvious when I just say, yeah, I study urban soils. Maybe you can imagine different aspects. Yeah, it can be any soil within a city. And then, of course, the question: and what about soils in villages? Yeah, are they also urban or anthropogenically changed, or they are natural, or they're quasi-natural? So there's always a discussion, and of course, in any city we can find a place where soils are not really disturbed, so they look like natural, or maybe they can be considered almost natural. So in this regard, there are many definitions. If we talk about classification, yeah, or Southern, which is internationally considered, then in WRB, the World Reference Base, there are two definitions for anthropogenic soils: anthrosoils and technosoils. These are the RSG, the reference soil groups, like huge groups of soils. There are in total 32 soil groups, so two of them are anthropogenically modified, let's say, and anthrosoils are more agricultural, and technosoils are described like soils formed at the primary soil formation stage by, let's say, with lots of artifacts, etc. And yeah, we usually talk about that we work with technosoils, but of course, also not all urban soils are technosoils. Like soils of green infrastructures are quite often not technosoils, or at least with not a such definition. So in this regard, we have sweet mass, yeah, soils of urban, industrial, traffic, mining, and military areas. That's a broader definition. And there are some national classifications, like in Russia or in Poland. There are more detailed classification where, let's say, soils of parks and soils of residential areas and soils of industrial sites. So they are from different domains. But let's say the basic information, which I think works for any urban soil, will be that they are manufactured, which can range from manufactured to man-made. They are very heterogeneous. Yeah, in average, they are always more heterogeneous than natural and agricultural. They are usually young. Yeah, so when we talk about the relative age of soils, then urban soils are almost always younger than the natural. They're all, or they're, that's why, or let's say as an additional indicator, they are very dynamic, so they change fast. And usually the younger is the soil, the faster it changes. And they are affected, or sometimes they are constructed for the particular function. So we can make a soil for sports, yeah, or we can make a soil for the backyard, for the playground. So we always keep in mind some particular function. In this regard, they can be similar to agricultural. They also have a particular function, but this is a different function. And yeah, for natural, they are way more likely multifunctional. Well, these are just some books and classifications of urban soils and different type of the urban soil profiles and horizons. So you can have this in mind when you try to describe an urban soil profile in field. Yeah, well, with Soils Within Cities book was edited by Maxen, and two others are, let's say, elder Russian classical books on urban soils, also quite interesting, I would say, for those who are Russian reading. But let's just make kind of the summary, like what is specific about urban soils? Well, first of all, as we mentioned, spatial variability. Imagine that urban soils can be made, well, almost from whatever you want. Yeah, once we made an analysis of the market of materials which are used, which are available in Moscow city for urban soils construction, and we came up with a list of more than like 100 names. Yeah, there were some composts and pits and mixtures and demolished urban wastes, urban building wastes, etc. So, but there are, let's say, huge choice, yeah, huge variability, and of course, dependent on how this choice is controlled, you can make an idea of, can you predict the urban soil's properties, or they really can be the almost anything. Besides, urban soils are more patchy than natural or agricultural. And when you have a look on, on Google Map or on a remote, on the satellite image, you can see that there are lots of small patches in cities, like small backyards and a park in between, and then a road and a parking slot. And of course, you can expect that under those patchy land cover, soil properties will be also quite variable, and probably with abrupt boundaries in comparison to natural conditions. What is also interesting that urban soils, they, on the one hand, are strongly affected by the current management, let's say by, again, green or industry, but at the same time, they inherit properties from the natural soil. And this is especially evident when you compare urban and natural soils from different climate or pediclimatic zones. In 2019, we, together with Maxine and, other SUITMA colleagues, we organized a summer school when we traveled from the very north of the European Russia to the south, from sea to sea, from Barents Sea to almost to the Black Sea. So we crossed several soil zones, and in each zone we compared natural versus urban. And this is what you can see. The top row are natural and the lower bottom row are urban. And of course, they're all different. So you would never really, or you will hardly mix up the natural and urban soil. And also urban soils, in urban soils, you can see some natural features like the buried horizons, for example. And you see that the very south and the very north examples are very different. But at the same time, there's always something similar, like artifacts, bricks, straight boundaries between the horizons. And if you add some chemical properties here, you will also see that most of them, for example, have neutral pH or heavy metal contents can be higher than in natural, etc. So basically, this is so-called convergence theory, convergence property, that urban soils are more similar to each other than the corresponding natural soils. What is also interesting that urban soils, they are exposed to a long-term anthropogenic effect, and this effect is kind of the reflected in urban soils profiles, especially when you talk about urban soils in ancient and medieval cities. I don't know if you can observe this in US a lot, but in Russia and also in Western Europe, especially in the northern part, if you make an excavation in the center of the city, you will likely get, let's say, several meters of paleosoil. And this paleosoil is very interesting in terms of chemical composition. For example, I've read a paper from our colleague from China, Ganlin Zhang, who made a analysis of and his paper was called 2000 years of metal industry in China. It was based on just one soil pit, because when you went deeper, you could observe the metals which were accumulated, let's say, in medieval times or in ancient history, and dependent on what kind of metal industry dominated, of course, the composition and the concentration was also different. And pretty much the same we can see with the carbon stocks, and I will focus on that a bit later. But even with this picture, you can see that the layer, the 4 meters, is pretty dark, and it clearly has enough carbon. And we can also try to see like where this is coming from. And there is a light layer and there is a dark layer again. But let's say the urban soil profile, especially in the city center, is kind of the chronology of, well, many factors, but one of the processes which is reflected is different stages of carbon accumulation and carbon storage. Urban soils are very heterogeneous and spatially dynamic, and you can easily see it by any example of the reconstruction of urban green space, or well, of any area, but let's say we focus more on urban green spaces. This is the case from one of my bachelor students when she actually mapped soil properties in a park before and after reconstruction. Only 2 years passed, was 2012, 2014, and this is the map of pH, but she also mapped other properties. And you see that not only the mean values, but also the spatial patterns were really different. Yeah, well, for topsoil, but also for 30 to 50 centimeters. So basically, urban soil management and maintenance of urban green infrastructure, and especially reconstruction, reorganization of green spaces, and they are well, happening almost continuously, they affect urban soils properties seriously. But although all these specifics, all this information is known, or at least we can agree that they are there, we still lack special information about urban soils. So if you go to global or regional soil map, and try to get understanding of the spatial variability of urban soils, likely it will not work. Yeah, well, depends. There are some maps of urban soils, or let's say of urban soil properties. For example, there are more and more maps of heavy metal distribution in urban soils, generally of urban soil pollution. But very often you will see stuff like that. Yeah, well, this is the map, soil map of Moscow region. It's a pretty old map from 1993 and not very accurate. It's 1 to 350,000. But Moscow city on this map is just gray. So basically, you don't know anything about urban soils. And yeah, I did not add it to this presentation, but if you would open the soil map of the Netherlands, and this is more or less at the same time, it was finished also in the 1990s, but it's more accurate, it's 1 to 50,000, you will see pretty much the same. Yeah, well, no idea what's going on with soils of Amsterdam or Wageningen. So that means that and if you go to the global source like soil grids, yeah, very highly accurate global resource with the 250-meter resolution, all urban soils are also gray because they're just masked. Yeah, there are no or almost no data from there, and they are not included in the grid model, soil grid model. So yeah, urban soils, at least in most of the properties, and especially in terms of carbon, they remain almost unknown. We need this information. Yeah, this information can be used for sustainable urban planning, for sustainable urban development, for at least assessing the potential of urban green spaces to capture carbon, but this information is not there. So that means that there are opportunities for us as researchers to get this information, to get an idea of what's going on happening with urban soils and urban soils carbon. It can be done in different scales and by different methods, and I will briefly describe you some case studies which are different in methods and stocks and fluxes. So these are the basic stocks and fluxes. We can go for organic carbon, inorganic carbon, black carbon, and in terms of the fluxes, we usually deal with soil respiration and subdivide it in microbial and root respiration. But when we focus only on greenhouse gas emissions, we can also study methane emission or N2O emission. Well, as for the special scales, yeah, they range from local, like you can study urban soils of your garden, to global, yeah, city level, regional level. And yeah, with the upscaling, so the higher level you get, the more difficult is to find the relevant indicator, and the indicators will change a lot. So if at the local scale you can work with the dynamic indicators, you can measure like soil respiration continuously, you can investigate soil microbial community, then at the global and regional scale, it's more and more challenging. So let's go through 4 case studies. Yeah, I guess we shall go fast to try to be in time. So I will just give you a general idea and share the presentation, and there are papers on each of those. So the first one was a very local study. We wanted to know how different design of soil construction, so basically the depth and the material used for soil construction, very small one, yeah, like less than 1 by 1 meter. How can this affect carbon stocks in perspective of several years? Because these were like the new constructed soils. We started from zero moment and we wanted to see what's going on. These are the results of the 3 years experiment. So the emissions were more or less following the seasonal trends with a higher emission in summer, low emission in winter. That's what we normally have in temperate climate. But carbon stocks, they rapidly went down after the first year. So they decreased like 2 times. And then they were kept decreasing, but with a less magnitude. And finally, they more or less stabilized at the values which were comparable to natural. So basically, the young technosols were quite serious carbon sources. Yeah, they emitted a lot. And what is even more important, that this emission was not compensated by carbon sequestration, because these were soils with lawns, with grasses, and of course grasses also grew and accumulated carbon, but that was not enough. Yeah, we calculated biomass in grasses, biomass in roots, and still emission was way higher. Well, there were some other curious outcomes. For example, the biggest difference between emissions and biomass was for the most shallow urban soils, because you can also make urban soils with 5 centimeter or with a 20 centimeter. And we showed that for 20 centimeter, it is theoretically possible to reach carbon balance. We haven't reached it, but for 3 years, but at least we saw the trend. And for 5 centimeters, we saw the opposite trend. So actually the difference of the gap between emissions and sequestration was growing. So we can expect that at some time those soils will just disappear, I mean, in terms of the carbon. This is another case which describes how carbon can be sequestered and stored in the deep layers, in the cultural layers I mentioned. This is an excavation in the center of Moscow near Kremlin, not so far. And this is excavation also 4 meters deep. It was described together with archaeologists, because all the time the cultural layers are described with archaeologists, and it's quite a nice story to see like where all these artifacts are coming from. But in terms of carbon, you can see that the highest stocks were described not for top layer as you would expect, but the highest stocks were for the layer below 2 meters. And what is also interesting, that the half-life time, and half-life time is kind of the how biodegradable are soil carbon stocks, how biodegradable is organic matter. Half-life time was also pretty low at the bottom horizons. So that means that if those layers are excavated and let's say stored at the surface, then we can expect very intensive emission. And sometimes this happens. For example, we made this excavation, then the Moscow center was reconstructed, and some of those layers were excavated and used for greening because they look, black and full of nutrients. But in fact, we would expect that technosols composed from these layers would be really non-sustainable in terms of carbon, because the potential emission can be very high. Moreover, we estimated like how much carbon is stored in those soils, and we tried to model the, let's say, the rate, the speed of this accumulation, and came up with this kind of number showing that more or less 20 to 30 kilograms of carbon per square meter are stored in each meter per century, and that's quite a lot. Another scale of analysis, when we try to compare how stocks and fluxes are different between the functional zones, for example, between the park and between the residential area. That was done for the central Russia, for the steppe conditions, and we also observed it for several years. And we showed that actually the ratio between emissions and stocks, the same condition, the same parameter we analyzed for the constructed technosols, was also very different. So basically, the part of the carbon stocks which were emitted, which were biodegraded in urban soils was way higher. And moreover, this fraction increased in the warmer years. So basically, urban soils were less resistant in terms of the carbon stocks, and this resistance went down when the, let's say, climate conditions were hotter. So we can expect with the global warming, the situation will get even worse. And this is how the profile distribution of the microbial respiration was studied. The next level is already the regional level. We worked with Moscow region. That's quite a big region of 46,000 square kilometers, quite diverse in terms of soil conditions. And we analyzed towns from different soil zones and made a representative data set actually to make a map. Yeah, we worked with the digital soil mapping approach when you project soil carbon based on environmental and urban specific factors, auxiliary data like soil seeding fraction or again functional use. And these are the resultant maps. So you can see that actually those settlements, yeah, which also did not cover more than 10% of the total area of the region, they were the hotspots of carbon stocks, and what is also quite interesting, of variance in carbon stocks. So the lower maps are the maps of coefficient of variance. They show how variable are stocks per unit, let's say. And we see that in cities, the coefficient of variance was higher than elsewhere. So we don't only have high carbon stocks in cities, but they are also the most variable. And then we did the same map for soil respiration and came up with a more or less similar conclusion. Can we expect the similar patterns when we move to the global level? Because at the global level, we likely will see how climate zones, let's say, are different, and how these difference affect carbon stocks in cities. This is, yeah, possible to do. Yeah, and anyway, the final global models are based on the point data collected at the local and regional scales. So depending on our focus, we can benefit from different ways of analysis, from different analytical methods. For example, if you work with a just soil sample, for example, you want to see whether a particular soil construction can be more or less resistant to climate change, the possible analysis can be based on basal respiration, which you can do in the laboratory under different climatic conditions, like under different standard temperatures, and predict half-life time. For example, we can show that the half-life time of urban soils can be very low. That means that the resistance of carbon stocks is also low. When you work at the city level, for example, you compare the central part to the suburb, you can see the effect of the mesoclimatic conditions, yeah, the urban heat island, which we mentioned in the beginning. For example, we showed that soil respiration in the city center is almost 30% higher than at the suburb, and this is caused by extra heat, because also the temperature was 2 to 5 degrees higher, and the moisture was lower. So you can talk about urban heat island, but also urban drought island effect. Yeah, well, this is kind of the approach we did for the Moscow, where we tried to link urban heat island to soil organic carbon and better respiration. I probably will skip some details, but let's say we made a map of soil organic carbon, then we made an experiment how soil respiration depends on organic matter and temperature, came up with a regression model, and then used the regression model together with the mesoclimatic model. So basically the model which makes a quite detailed map of surface temperatures and soil moisture. And in result, we generated the, let's say, set of maps of soil temperature and moisture, and together with the soil carbon map ended up with this map of soil respiration. And when you have both, when you have soil respiration and soil carbon stocks, you can easily calculate the half-life time, which basically shows you where are the risk zones, where are the most vulnerable areas for carbon emission. And we showed that for Moscow, the most vulnerable areas were exactly in the center, because on the one hand, the urban heat island there was the strongest, and that was obvious, but also it coincided with the young, recently made technosols, and they were made from material with a high amount of carbon, like with a peat or with a compost. And those two factors resulted in really high risks of emissions because the half-life time was really low. And that was our message for soil management in the city. And we even estimated those additional CO2 emissions from the effect of urban heat island, and that was pretty high, like about 25% of total. If we try to put together the experience we have from different cities globally and make kind of the review of what's going on with the urban soil carbon in different cities of the world, we try to do it in a review paper, and we made kind of relationship. We, for example, figure out that in the north, urban soil carbon is more resistant and it's higher than soil carbon in natural conditions, whereas in the tropical and subtropical regions we can see the opposite. We also checked this assumption by regional study in the Central European Russia. That was the summer school I referred to. So we moved from city to city and analyzed carbon stocks and soil respiration there. These are the soils we discussed, and these are the main outcomes. So basically you see that inorganic carbon was going up from north to south, whereas organic carbon and also half-life time went down. So basically in the most south conditions, where the natural soils are chornosomes, which are really rich in carbon, in cities you can expect the lowest stocks due to the low resistance to biodegradation and to climate change. And we also compared two seasons, two summers, summer of 2020, summer of 2021. 2021 was considerably hotter, and we also saw the peak in soil emission. So there was kind of a very strong relationship. Sorry. So I think that we are getting to the end in terms of the time, also in terms of the lecture. And I bring you back to the message which I started from. So we need information about carbon stocks and fluxes from urban soils. We don't have this information, or let's say we lack this information, but when we get it, there are lots of ways to implement it. This is just kind of the idea of tools which are already available for landscape planners and for urban planners, which propose to consider urban soil somehow, and they also have some idea of soil carbon, but let's say so far scientifically it's pretty vague, but even in this condition it is used. So we can imagine that when we have the more detailed, more accurate data, these kind of tools or more advanced tools can be implemented. And if I were, let's say, an engineer of this kind of tool, I would come up with this kind of concept which shall bring together local and regional drivers, social and environmental factors, and their effects on carbon stocks in urban soils. That's pretty much it. Thanks for the attention, and I leave you with the picture of our campus and some figures from our paper, which we are now working on, because this is the paper about soil organic carbon stocks in the university campus as a living lab for urban green infrastructures.